Hello everyone. Thank you for being here. My name is Niham, and today I'm going to be talking about my work SmokeSeer, which extends 3D Gaussian splatting to do wildfire scene reconstruction and smoke removal. This is work that I did during my master's thesis at Carnegie Mellon University, and I presented this work last month at 3DV. And this is work done in collaboration with Yanis, Sebastian Scherer, and Andrew Jung. Um, so over the recent years, wildfires have intensified dramatically, driven in part by global warming and other environmental factors. Uh, the wildfires in LA, like a couple of years back, they claimed the lives of 29 people and caused economic losses of around $106 billion. So to motivate our work, I would like to show a couple of videos of people on the front line fighting fires. And on the left, you can see that people are trying to desperately escape, like escaping a wildfire scene. And on the right, you can see firefighters trying to navigate like harsh conditions and trying to contain a wildfire. So currently these responders like wait for the smoke to clear before planning their next move, which costs like a lot of precious time. And having some sort of granular situational awareness in these conditions is very important for their safety. So this critical need for fast and reliable reconnaissance is the primary motivation for my work. And we want to give firefighters and robots the ability to see through smoke, improving safety, decision making, and save lives. So this was a big project at CMU, which comprised of 3 labs trying to build the tech to accomplish this task. And like my work presented in this talk is going to focus on the desmoking and the 3D reconstruction side of things. So the setup of the problem is this. Given the RGB footage of like a forest or like a scene on fire and the corresponding thermal video of the scene, we want to do a simultaneous desmoking and 3D reconstruction. And this can help downstream applications such as object detection, image segmentation, and 3D reconstruction can enable precise spatial reasoning and path planning for robots in complex scenarios. So before diving into the details, I'll provide like a brief background on 3D Gaussian splatting. So we are trying to solve the inverse graphics problem. Given 2D images of the scene, how can we infer the camera poses and reconstruct the underlying 3D environment? So we start with a scene representation, which is our current guess of the scene's shape and appearance. And we feed this into a renderer, which converts it into a 2D image. And because this rendering process is differentiable, we can compute the difference in pixel colors and backpropagate it to adjust the scene representation. So compared to voxel grids or neural networks, which are used in nerve, 3D Gaussian splatting takes a more sparse approach, and it represents the scene only at locations where there's actual content or like non-zero density using like a set of 3D Gaussian blobs. And each Gaussian has like a position, a size, a shape, and a color. And by parameterizing the radiance field only where it is present, we avoid wasting effort on empty space. And one good thing about 3D Gaussians is that it's a volumetric representation. And this is particularly well suited to our problem because it can model both the surface and the smoke part of the scene really well. So to project these 3D Gaussians and convert them to an image, we project them onto the image plane using the mean and the camera projection matrix. And these contributions can be accumulated using alpha blending to produce the final color. And 3DGS uses rasterization to render out the image, and this rasterization is done through some extremely efficient CUDA kernels, which can make the rendering real time and the training process much faster. So as we optimize the positions, size, and colors of these Gaussians, this allows us to capture both the geometry and appearance of the scene. And this allows us to render realistic views from any camera angle. So you can see the Gaussians on the right, which are like representing the scene in some way, and you can convert them to an image. So I'm going to give some mathematical background on how we actually disentangle the scene into its two components. So we want to kind of do a disentanglement and convert the scene into the surface component and smoke component. And once we do it, we can kind of only get the contributions from the surface part of the scene and do the desmoking of the scene. So the C surface, it's parameterized by a color C and a density sigma. And the smoke part of the scene, it's parameterized by CS and sigma S. And the transmittance term, it's computed from both sigma and sigma S. So the transmittance, which is the attenuation coefficient, it includes both the absorption and the outscattering effect of the smoke. So the main takeaway is that we want to disentangle the scene into two distinct set of Gaussians, one representing the smoke part of the scene and one representing the surface part of the scene. And rendering the union of these two sets is equivalent to rendering these observations that we have. And once we have done this disentanglement, we can just render the surface part, surface Gaussians and remove the smoke from the scene essentially. And once you have learned the smoke Gaussians, you can render out to get the smoke part of the scene. So performing this decomposition or this disentanglement using just RGB images is challenging due to the light scattering smoke particles. And to address this challenge, we leverage thermal cameras, which are substantially less affected by scattering and smoke, as you can see in the video. Like the RGB image is completely smoke filled, and like thermal, you can basically see through the smoke. So me theory provides like a theoretical framework to quantify the scattering of the smoke particles as a function of wavelength. So RGB cameras operate in a wavelength of 400 to 700 nanometers, which is like 0.4 to 0.7 micrometers. And thermal images, they operate at a wavelength of 8 to 14 micrometers. So you can see that the scattering represented by this green rectangle, you can see that the scattering is much less. So like our method can leverage the color information from the RGB images, and it can leverage like the spatial information from thermal images to do joint RGB thermal 3D reconstruction. And leveraging these complementary modalities can make the 3D reconstruction more robust and useful to firefighters. So to model the smoke and the surface, we extend the original 3D Gaussian splatting. So each Gaussian now has two sets of spherical harmonics, one to represent the RGB part of the scene and one to represent the thermal part of the scene. So it has two sets of colors essentially. So for the surface Gaussians, there's only a single set of opacity, which is like the transparency value. But since the scattering properties of smoke across RGB and thermal are so different, so we need two sets of transparency values for the smoke part of the scene. But for the surface, we can share it. Also, we assume that the surface is static, but we assume that the smoke is moving with respect to time. So we have some time varying properties for the smoke Gaussians. So 3D reconstruction methods such as Gaussian splatting, they treat pose estimation as a solved problem. They rely on call map or more like master SFM to get a pose estimate. But in our case, call map fails to register most of the images. So we have to create like a custom pipeline to estimate the poses. And in stage 2, we just do the surface reconstruction using the thermal images. And in stage 3, we fuse in the RGB information and explicitly model the surface and smoke Gaussians. So you can, in this photo, you can see like the SIFT feature extractor, which is used in Colmap. And you can see that the matches that you get, like they're very low quality. And you can see master, which is like a learning based technique. And you can see that the matches that you get are much better, uh, like much better in terms of quality. And since you're doing joint RGB thermal reconstruction, we also need to do matching between RGB images and thermal images, since we're doing joint reconstruction. And again, SIFT doesn't work well. And we observe that minima, which is like a technique, feature matching technique, like designed for RGB thermal, like cross infrared matching, like that performs much better compared to master SFM and SIFT both. So our pipeline looks something like this. We do master SFM on just RGB images and just thermal images. And then we use these use minima as an alignment module to get the poses and point cloud in the same coordinate frame. And in the second stage, we do the surface reconstruction using uh, just the thermal poses and point cloud that we did in the last scene. So this is vanilla 3D Gaussian splatting, and we get like a coarse surface reconstruction. And in the final stage, we introduce the smoke Gaussians and incorporate the RGB images into the optimization. Um, And we also have a MLP to model the dynamics of the smoke. So this is standard 4D Gaussian splatting literature where we feed in the position of the Gaussians into the MLP and predict like a deformation field. Um, so we know that the union of these two sets, when we render it out, we have the observations already. So we can use like a rendering loss to back propagate onto the weights of the properties of surface and smoke Gaussians. And additionally, we place some priors on the surface Gaussians, which is like the monocular depth loss. So these are like priors that we get from foundation models like depth anything V2. And we also get masks for the smoke using SAM V2 or something like that. Um, Also, we know that the smoke Gaussians have like a similar color and similar opacity and they're monochromatic. So we can minimize the variance and place that as like a additional loss function. And once we do that, we can render out the surface Gaussians and we can see that the surface part of the scene is obtained. And we can see that the uh, upon rendering the smoke Gaussians, we get like the smoke part of the scene. So when I first started working on this problem, there were no data sets to evaluate this particular task. So we had to create like a synthetic data to validate and evaluate this particular task. And we use Blender, which is like a 3D modeling software to simulate the smoke. And Blender has like a MantaFlow plugin which simulates the physics of this smoke to produce like a very natural smoke movement. And since it's like a simulation, getting like ground truth information is also much easier. So we can experiment with like different smoke densities and motions of the smoke in like a controlled manner. So these are some of the data that we simulate in Blender. So we simulate both like object level and scene level data and like moving on to the results. So you can see the fourth column, which is like our reconstructed surface. We are able to like get most of the like remove most of the smoke, but the color is still not that great because of the inherent ambiguity between like light scattering and color attenuation. But ultimately, we wanted to test our algorithm on real world data. And so to collect data in real life, we had a handheld setup. And through this setup, we could collect data on a smaller scale outside CMU campus. And we also had a testing site called Allegheny Fire County Academy. So this was in collaboration with the local county's fire department. Oops. So we could use their testing site to set off some smoke bombs and collect data using a drone. Um, yeah, so these are our results on the real world data. Oh. Yeah, I think we are able to remove like most of the smoke, but there's still some artifacts. Yeah, and this is another scene where we collect data and use our algorithm. Yeah, that's all from my side. Thank you so much, and I'm open to any questions.
Thank you, Niham. Yeah, there's a few questions here in the Q and A, and if anybody in the audience has questions, feel free to drop them in the chat or drop them in the QA while we have Niham up here. But first question is, and I guess you kind of touched on it towards the end there,
Mhm.
but just to ask it, how was the real world RGB plus thermal smoke dataset captured, and is there paired smoke-free ground truth for each scene?
Yes. So so the drone that we have in the video here, that has like a RGB and thermal payload. Um, but sadly, the payload doesn't have time synchronization between the RGB cameras and thermal cameras. So there's a slight offset between the frames of the RGB camera and thermal camera. That's why we need to do the procedure that I described in step one, where we have to uh, where we have this custom pipeline for obtaining the poses. Um, and talking about the ground truth, since yeah, obtaining ground truth for this particular task is kind of challenging because you kind of need to fly the drone in the entire same trajectory and capture at the exact same time, which is almost impossible. So in practice, what we do is that we do a 3D reconstruction and of the smoke filled video and the non-smoke filled video, and we get the poses in the same coordinate frame, and then we try to do like some novel view synthesis. That's why they aren't exactly aligned, I would say. Um, so yeah, that's how we obtain this pseudo ground truth.
Okay. A question here, I guess. It's a nice slide to have it on here. It's how much does the thermal channel actually buy you? Did you ablate RGB only versus RGB plus thermal? And where does each modality fail on its own?
Yeah, we have some experiments in the paper that try to uh, like uh, do like ablations on this, and we find out that like the thermal helps a lot. Like I think since the stage one is completely like the surface is completely initialized using the thermal images, we find that the thermal information helps a lot in getting like the de-smoke done. So and I think adding RGB to that helps the surface a little bit because thermal images are very low resolution in nature. So adding RGB to that does help the geometry and the surface part a little bit. Um, and the color is completely obtained from the RGB, of course. So
Okay. And the final question here is, did you investigate the failure modes? Was there any particular kind of smoke or scene that breaks SmokeSeer?
yeah, I think since this is an optimization algorithm, like and not like a learning, like doesn't rely too much on learning based priors, like if the smoke is very thick or very fast moving, like our pipeline kind of breaks. So it would be interesting to see in follow-up works if you can leverage some generative-based techniques to kind of tackle this problem.
Awesome. Thank you so much, Niham, for the presentation and for taking on the questions. And it was great
Mhm.
meeting you at 3DV. We'll